Trig, section 5.2, verifying trig identities. We're not going to learn any new trig identities this time, or this section, but we're going to learn how to use the ones we already know. The rules, if you remember from geometry, if you did your constructions with a straight edge and a compass, there were rules for that. Your straight edge could have no markings, or at least you couldn't use them to draw. You just needed a straight edge to draw a straight line. Your compass you could change to different lengths, but those two things, straight edge and compass, were all you could use when you would prove or show that a geometric theorem was correct. Now we're going to have rules for verifying identities. You could have different rules, but these are the ones we're going to use. And, of course, if I don't learn how to do this, let's move this back up again. Okay. Rule number 1. Can only work on one side. Now, you can look at the other side, certainly, and you can think about the other side, but technically, only one side can be worked on. You have to change that side. Verifying identities is really changing one side into the other. And so you have to change that without working across the equal sign also. What does that working across the equal sign mean? Well, that means you can't multiply both sides by the same thing. You can't add both sides, the same thing to both sides. You work on one side, so you're really multiplying by ones and adding zeros, whatever that might mean. Multiplying by ones could be 5 over 5, could be sine theta over sine theta, whatever you might need, but that's all you can multiply by. Now you can write reasons, but you must take baby steps. Baby steps means you can't all of a sudden get the answer. It doesn't going to work. The answer you know because it's the other side of the equation. You've got to show me, so that I can follow it, what steps you took logically to get there. So, you can write thought bubbles. Now I'll show you what thought bubbles are, but it's sort of like when you have cartoons or comics. That's the speaking bubble. Yours can be thought bubbles. There's not usually just one answer, so these are going to take longer for me to grade on a test, but your answer may look different than another person's answer, but logically you arrive to the same conclusion. I have to be able to read it though, and so we're going to use a bunch of examples to show you then how I want things set up and how the rules, how they apply to all these problems. So there are hints on page 203, that green box. So that if you want some hints, that's a good thing to look at. There are cautions on page 202. But really what this is going to take is some practice. So let's start with an example. Number 22. Not sure what page this is on, but first of all, the directions simplify, and they want no quotients. So sometimes these simplify are just not enough directions for us. We're going to rely primarily on verifying these identities because that is pretty straightforward and you'll know what you need to get. So if you're given 1 over sine alpha minus 1 and subtract from that 1 over sine alpha plus 1. For these types of problems, they're going to want you to combine these two into one and try to write these with no quotients. So you're going to have really down to maybe one trig function, but maybe not. Your answer may be a combination of trig functions also. So, in order to combine fractions, we need a common denominator. A common denominator needs to include both of these denominators. So, I'm going to take the sine alpha plus 1 and multiply this side times the 1 over sine alpha plus 1 times the sine alpha minus 1 minus, then I'm going to take this one, sine alpha minus 1 times the 1 over this sine alpha plus 1 times sine alpha minus 1. I'm running out of room a little bit, but these have a common denominator, so the sine alpha plus 1 minus, well, I better be careful with this subtraction, sine alpha minus 1 over that common denominator of sine alpha plus 1 times sine alpha minus 1. Don't multiply those out unless it's going to help you simplify this. Let's see here. In the numerator, we've got the sine alpha plus 1 minus sine alpha. So the sine alphas are going to cancel. But the plus 1 and the other one, which was subtraction and now it's addition, is going to make it into a 2. The sine alphas cancel. But we have plus 1 minus a negative 1, which is also plus 1. That's over this. Now, let's see if we can say, okay, if I can't have a quotient, I'm going to have to somehow get rid of this. So let's multiply this out. Remember the difference of two squares, product, a plus b, a minus b. That's equal to a squared minus b squared. That's going to work here too, a plus b, a minus b. So it's a squared, or sine squared alpha, minus b squared, which is just 1. So let's see here, sine squared alpha minus 1, this is our thought bubble here. Sine squared alpha minus 1 comes from our Pythagorean identities. Sine squared alpha plus cosine squared alpha equals 1. So if we do a sine squared alpha, subtract 1 from both sides, and put the cosine, which is negative cosine squared alpha, on the other side, then we can use that. That's another thought bubble. So now we can write this as 2 over a negative cosine squared alpha. Well, we're not supposed to have quotients. So what is 1 over cosine? Well, that's the same as a secant. But we need the negative, we need the 2, and it's not just secant, but secant squared alpha. That is our final answer. And what they're trying to get you to do with these problems is be able to combine things with your trig identities, get it down to one just trig function maybe. So if we're supposed to factor this, sine cubed alpha plus cosine cubed alpha, let's think about this a little bit. This is like, if you recall from algebra, this is like y cubed plus x cubed. Remember how to factor those? Well, let's think of this also as box cubed plus triangle cubed. I think that, because you can put anything in the box of the triangle. So this factors into box plus triangle times box squared minus box triangle plus triangle squared. In other words, take the cube root of the first, this would be y, and the cube root of the second, this would be x, and say y plus x, and then it's y squared minus yx plus x squared. That works for anything, even sine alpha cubed. So let's put it down here. It's going to be the first sine alpha plus the second cosine alpha times the first one squared, sine squared alpha, minus, remember this sign is always the opposite, the product of the two, sine alpha cosine alpha, plus, always plus, the cosine squared alpha. Remember SOAP? This is the same, this is opposite, this is always positive. So, if this were subtraction, this would be subtraction, opposite would be addition, this one's always positive. So you can do the sum or difference of two cubes factoring. These factors may be necessary for figuring out a trig identity. So, we can take this a little further if we want to, and you really don't know that until you know when to stop, and you'll have to know the answer for that. So this is still sine alpha plus cosine alpha, but now let's put that sine squared alpha plus cosine squared alpha together minus sine alpha cosine alpha. But what is sine squared plus cosine squared? That's a Pythagorean identity. That's just 1. So we get sine alpha plus cosine alpha times 1 minus sine alpha cosine alpha. That's as far as you can really do this one. And that was in the back of the book. So sometimes you look it up in the back of the book and say, this is where I got to get to. So this is problem number 44. What we're supposed to do is rewrite this 1 minus 1 over secant squared x as a constant, or maybe a single function like sine or cosine or tangent or whatever, or the power of a single function, sine squared, cosine squared. How do you do that? You just start working on it. In order to combine two things when they're fractions, you must have a common denominator. So this 1 we're going to change to secant squared x over secant squared x. That's what you're going to know an awful lot in order to use 1. This is 1 over secant squared x. Now you combine the numerators, secant squared x minus 1 over that common denominator, secant squared x. Now remember, you cannot cancel these secant squareds. This has got subtraction, it's got to be multiplication in between. Addition won't work either. But secant squared x minus 1. Boy, I remember something. One of our trig identities, Pythagorean, tangent squared x is plus 1, or 1 plus tangent squared x, doesn't matter which, is equal to secant squared x. And that means that tangent squared x is equal to secant squared x minus 1. Maybe that's what you were thinking about in your thought bubble. So this numerator becomes tangent squared x over secant squared x. Oh man, well that's close. It's got to be a single function though. Well, we're going to have to squeeze this in. I used too big a thought bubble. Tangent squared x is really sine squared x over cosine squared x. And secant squared x is 1 over cosine squared x. Now, when you invert this denominator and multiply, you get sine squared x over cosine squared x times cosine squared x over 1. The cosine squareds cancel, and you are left with sine squared x over 1, of course, but that's the single function, but a power of a single function. Does that make sense? So this thing down to sine squared x. Okay, here's the verifying an identity type of problem. We have these two sides, these two expressions equal to each other. You're supposed to verify that. You're supposed to prove that it's true by picking one side, doesn't really matter which, and turning it into the other side. Exactly. So, how do you choose the sides? Normally you choose the more complicated side. In this case, even though the right side has a fraction, it's got these sine alpha trig functions, where on the left side it's got the secant and the tangent. Most of our identities are used to taking these secants and tangents and changing them into sines and cosines and stuff. So I think it'd be easier to do it with that here. So we're going to work on the left side. Now we're going to keep worrying about the right side, but we're not going to touch it, so to speak. So secant is 1 over cosine alpha, and tangent is sine alpha over cosine alpha, and that's squared. So it's easier to square a single fraction. So let's see. This has a common denominator for cosine, so 1 minus sine alpha over cosine alpha quantity squared. So now we can square both of these. We'll square the numerator, 1 minus sine alpha quantity squared over cosine squared alpha. Now let's see here. Now before you multiply things out, let me see, because do we want on the right side? We need just 1 minus sine alpha. We've got two of those here. We've got, times each other. We need to cancel one of those. So I'm going to use this cosine squared and write it. Let's see. We've got 1 minus sine alpha quantity squared over cosine squared is 1 minus sine squared. We're going to use alpha because this is a trig identity, the Pythagorean identity. Now, usually you won't have to do this because you'll not run out of room, but I'm going to run out of room unless I do it here. We'll see if we can have room to write that down. But that's the Pythagorean identity. Sine squared alpha plus cosine squared alpha equals 1. Subtract sine squared from both sides. So now what does that numerator become? Well, it's still 1 minus sine alpha quantity squared. But we can factor the denominator. This is really a 1 squared minus sine squared, the difference of two squares. You remember how to factor those? It's the first plus the second, 1 plus sine alpha, times the first minus the second, 1 minus sine alpha. And that's what we needed, because one of these 1 minus sine alphas will cancel with this 1 minus sine alpha, and we have one left, 1 minus sine alpha, over 1 plus sine alpha. Now, when you're all done, when you make it look exactly like this right side up here, then what I'd like to see, just so I know that you know it's done, is write QED, which is Latin for quod erat demonstratum. something like that. It means that which was to be shown. It's got to look exactly the same. And you'll be done. So these are sort of nice problems because you know what the answer is going to be. You get to choose which side, but you've got to take this baby steps, make sure I can follow it, and probably this should have been a longer sheet of paper and have trailed down below this. It's better to keep it all on one side, and then when you're all done, sort of put an arrow up to this one. We'll see if we can fit one on here for you. Okay, another one of our problems here. Now, once again, you get to choose the side to work on. You can only work on one side. This is just a sine. These are cotangents. So these have more ability to sort of spread out and collect things and cancel stuff. Cotangent squared t is cosine squared t over sine squared t minus 1. That's over the 1 plus cotangent squared, which is cosine squared t over sine squared t. Okay. Keep these equal signs around down here. See if I can fit all this on. It's a little bit big. To combine fractions, you need common denominator. We're going to call this sine squared t over sine squared t. The same thing with this one. So, because I'm running out of room already, but we've got cosine squared t minus sine squared t over that common denominator of sine squared t. That is over sine squared t plus cosine squared t. Over the common denominator sine squared t. I hope I didn't skip too many steps there. This is where you got to use your judgment. Well, don't skip too much. And if you've got paper to show it, it's better to show it so I don't take off points. Okay. Now, because we got a fraction over a fraction, we can invert and multiply. So that cosine squared t minus sine squared t over sine squared t times, you invert this denominator, put the sine squared t in the numerator, over sine squared t plus cosine squared t. Now, a lot of things can happen here. Let me change colors. Well, I don't want to change too much. So, sine squared t's cancel. Put a line through those. That should show it. Don't scribble it out. The sine squared t plus cosine squared t is an identity that is just 1, the Pythagorean identity. So we have really cosine squared t minus sine squared t times 1, right? Because it's 1 over 1. Put that here, times 1. This is the 1. Now, I'm going to go and start another spot here. Oh, I don't want the equal sign there, though. But hold it. Cosine squared t is, because we just want sine squareds, is 1 minus sine squared t minus sine squared t. Does that make sense? This cosine squared t is 1 minus sine squared t minus sine squared t. This is times 1. So I really have 1 minus 2 sine squared t's. And that's what I was trying to get. Q, E, D. Once again, this should probably, all this stuff should probably be underneath this, but I ran out of room. Do it all down the same side here. And when you're done, then you can just go up and have your arrow point. Okay, you should be able to do all the problems from section 5.2.